The objective of this talk is to illustrate how to do the fatigue crack growth analysis that is necessary to assess the economic life of an additively manufactured replacement part. To put this in context, it should be noted that in March 2019, the memo by the Undersecretary, Acquisitions and Sustainment stated that the DoD will use AM to enable the transformation of maintenance and supply chains, increase logistics resilience, improve self-sustainment and readiness. He went on to state that AM parts can be used in both critical and non-critical applications. Structures Bulletin EZ 1901 subsequently outlined the United States Air Force requirements for the durability and damage tolerance certification for aircraft structural parts and AM repairs. Structures Bulletin EZ 1901 states that for structural parts that are manufactured using an AM process, the most difficult challenge is to establish an accurate prediction of structural performance. The airworthiness certification of AM replacement parts requires a durability analysis. As per the Joint Services Structural Guidelines 2006, the equivalent initial damage size, or EIDS, required for the associated durability analysis is sub-millimeter and must be greater than 0.01 of an inch or 0.25 of a millimeter. Lincoln in the United States Air Force was the first to highlight the importance of using the small crack DADN versus delta K curve in any sustainment analysis. If this is not done, then the equivalent initial damage size, or EIDS, becomes a function of the load spectrum. It is now known that for additively manufactured Ti-6-4, the small crack growth curve can be estimated from the long crack growth Hartman-Shivey equation representation by setting the threshold term to a small value, typically between 0.1 to 0.3 MPa root meter. In this context, we have established that crack growth in AM materials can be expressed as per equations 1 and 2. In equation 2, the crack driving force delta kappa is as first defined by Professor Schwalbe. For Ti-6Al-4V, the constants are given in the slide. In order to get the small crack growth equation from equation 2, you merely set the threshold value to be small. Examples that illustrate the ability to capture the crack growth behavior in two different materials are shown in this slide. One is Inconel 625, the other is 17.4 pH stainless steel. To continue this study, let us consider crack growth in wire and arc additively manufactured, or WAM, Ti-6-4 compact tension specimens. Here we see that there is excellent agreement between the measured and predicted crack growth histories for two different specimen tests. One of the important considerations when considering additively manufactured materials is how do you allow for the effect of the residual stresses. To illustrate this, consider the compact tension specimens shown in this particular slide, which were partially manufactured with WAM, connected to wrought Ti-6Al-4V compact tension specimens. This slide shows both the two different geometries and also the residual stress intensity factors that were obtained in the manufacturing process for these two different specimens. As we see in the slide, the Hartmann-Chivy equation has the attractive feature that it can accurately reproduce the effect of the residual stress field on crack growth in these two very different test specimens. Let us next consider how we can use the Hartmann-Chivy equation to predict the growth of small surface cracks in an additively manufactured specimen. The particular specimen and the particular manufacturing process are shown in this slide. The governing form of the Hartmann-Chivy equation that we'll use in this analysis is given in the slide by equation 3. This equation follows directly from slide 5, where we have set the threshold to a small value, in this case 0.1. Here, A is the apparent cyclic fracture toughness. We will use this equation to compute small crack growth history in two tests on additively manufactured Ti-6Al-4V specimens that were built using two different AM machines, namely Shaw 250 and EOS M290. The measured and computed crack growth histories using this formulation for the Shaw specimens, which were tested at 268 megapascals with an R ratio of -1, are shown in this slide. As you can see, there is very good agreement. The first measurable size in this plot is approximately 0.34 of a millimeter, and the fracture toughness for this specimen was round about 37 MPa root meter. The other specimen was built using an EOS M290 facility, and it was tested at 920 megapascals with R equals -1. The first crack size shown in this plot is approximately 0.19 of a millimeter, and the fracture toughness in the analysis was approximately 85 MPa root meter. And as you can see, there is again very good agreement between the measured and computed crack growth histories. Now summarize. The certification requirements for additively manufactured replacement parts requires an ability to accurately predict the growth of small sub-millimeter cracks. To this end, we've shown that the Hartmann-Chivy crack growth equation that was proposed in a prior paper for the growth of small cracks in additively manufactured Ti-6-4 reasonably accurately predicts the growth of small cracks in these two additively manufactured specimen tests. The initial crack sizes in this study are comparable to the equivalent initial damage size, or EIDS, in the United States approach to the certification of an AM replacement part. As such, we have shown how the Hartmann-Chivy equation can be used to compute the growth of small sub-millimeter cracks in AM replacement parts. Here, the initial crack sizes are consistent with those required in the Structures Bulletin EZ 1901 for a durability economic life analysis. Thank you very much for listening, and are there any questions?